is going to talk about reverse Monte Carlo fitting. Please let's welcome him.
All right, yeah, so this is somewhat related. So this is, oh yeah, I started the recording. Yeah, so this talk this has been mentioned at least in 2 other talks before, but I'm going to get into the details of it a little bit more. This talk is going to be a little bit shorter than the last one. But yeah, reverse Monte Carlo modeling of PDF data. So I mentioned yesterday a bit how you could do like a small box crystallographic type modeling. It's kind of like a detailed refinement in real space. There's also this reverse Monte Carlo modeling. It's something what's called the large box modeling. So I'm going to just go over kind of the mechanism of how it works, and then get into kind of the little details of how you actually set it up and run it, and all the little things you need to consider in order to make sure that it works properly. And then we're actually going to go through this afternoon as one of the tutorials. So RMC stands for Reverse Monte Carlo. What it is it's a global optimization method that uses random moves to fit a configuration of atoms to data. So you have a large box, and you're randomly moving the atoms around, and you're selecting certain ones to fit. And it's a very random process. And so important thing to keep in mind with this method is that it's going to produce the most random distribution that is still consistent with the data. So if you get any type of order out of it, then that order is probably real, but you always have to be keeping in mind that you could be missing some type of order that it's just not sensitive to. And so it's a very flexible and powerful method, but it's also something you have to be careful with, because if you're think about what you're doing with it, or else you could end up with nonsensical answers, because it's also, kind of like a stupid method that just fits everything. So first I'm going to describe exactly what the reverse Monte Carlo process is and how it works. So first thing you do is you make a large configuration of atoms, typically, tens of thousands. And then you're going to randomly move an atom, usually by a pretty small amount. And if the move makes the fit better, then that move is accepted. If it makes the fit worse, it could be accepted or rejected. And this is important because this gets you out of local minimum. If you didn't have this process, you would just go immediately to the local minimum, which is almost certainly not your global minimum. So this gets you exploring kind of the whole space, but still moving it towards a solution. And there's a value sigma, which is a very important value for RMC, which determines how much worse the fit gets, but is still accepted. So you can see here, the quality of the fit is measured by this value called chi-squared. And this is just basically, you sum up for all the data points, what is the expected versus the calculated, the difference. And then you're dividing that by the sigma squared. So if you have a big sigma, then you can accept a lot of moves, and if you have a small sigma, you're not. And the probability of a move being accepted is based on the change in chi-squared between after you move. So this difference in chi-squared determines the probability, and it falls off exponentially as the fit gets worse. So moves that make the fit a little bit worse are much more likely to get accepted than moves that make the fit a little bit worse are much more likely to be accepted than moves that make the fit much worse. And then you just repeat this process millions of times, and eventually you reach an equilibrium where the quality of the fit is just changing a little bit up and down, but it's not continuously moving down. And it's important to remember that you're not getting to a unique solution here. You're getting kind of to a unique distribution. So the configuration is changing, but the relative distributions of distances and angles and stuff is basically staying the same when you reach the equilibrium. So there's a lot of advantages to using RMC. There's also some disadvantages. So one advantage is that it's not constrained by symmetry. So you're not putting in any space group information or anything like that when you're doing an RMC. It's usually pretty easy to produce a starting model, at least with mostly crystalline materials. It's not so much based on your assumptions. So like when you're doing PDF GUI fitting, you're more taking a model, trying to fit it, seeing how it fits. So you more can come up with an idea, test it, and see if it is consistent with the data. For RMC, you just kind of let it go, and then maybe it'll come up with something you didn't even think of. You can also fit multiple types of data as constraints. I'll go into that more later. It can fit very complex systems with a lot of different local environments. So if you have, a whole lot of disorder and you have a big variety of local environments, you really can't do that with like a PDF GUI type refinement. You could also, and I think this is one of the most important, you can model you can have this configuration be consistent with a short, medium, and long range order, all within the same configuration, which is something you don't really do with PDF GUI. There was that boxcar modeling I was talking about yesterday, where you can fit different, you fit like the nearest neighbors with one model and then the long range structure with another one. And this can also handle amorphous or liquid materials that have no long range order, so that's a little bit trickier. The downside, of course, is it's very computationally expensive. Often you're going to run it for several days, and the interpretation is a little trickier because you end up, with like 60,000 atomic coordinates that you have to try to make sense out of. But there's ways to do that. So the thing about RMC is that you can use multiple types of data sets as input for it, and usually it's good to do that. So you can put in your PDF, your G of R, and you could actually do this for, if you had neutron and X-ray, you could actually put them both in and refine it against the same time. You can also put in an S of Q, or I think these days they're switching to using F of Q. You can also put in the Bragg data if you have a crystalline compound, and that has the advantage of it gives it sort of the three-dimensional information that you don't have in the one-dimensional PDF. You can also add in XAFS data. And then developers, I think they have plans to incorporate a number of other types of data like NMR, Raman, and TEM. So you can put a whole bunch of different data sets in at the same time to refine them, and you get out a single model. So to set this up, basically the first thing to do is to solve the average crystal structure is always the first step if it's a mostly crystalline material that you can describe by a crystal structure. You create starting configurations, you set up a bunch of input files, you have to format the data, then you run it, and then you have to interpret that final configuration. So first step, do a Rietveld refinement. So preferably, if you have a mostly crystalline system, is you do the Rietveld refinement on the same total scattering data that you're making the PDF out of. So here is like an example of a high temperature cubic perovskite, where this is collected at high energy, so it's not very sharp peaks, but it's a simple system, so it works fine. And then you have lattice parameters and atomic system based on the data. And then for crystalline materials, making the starting configuration is pretty easy. Usually you're just going to expand the unit cell, and there's a command to do that into just a big supercell that's a whole bunch of unit cells in a row. And a lot of this stuff you can also do, as Bob mentioned, in GSASS2. He's set up a thing where you can actually create these files from it. But if you don't, there's also a simple command to do it as well. And so you make a big box, and you have to keep in mind, too, that the PDF it will fit the PDF up to half the shortest distance of the configuration. So whatever the shortest distance of this big box is, it'll fit it to half that. And that's to avoid periodic effects, because this actually still uses periodicity. It just so that that atom on one side is connected to this one, so you don't have like some atoms that are just like dangling. But since it's really a really big cell, you get around it by just fitting the PDF at shorter distances than the periodicity happens. So there's a few additional steps you need to take if you have site disorder. So RMC profile has a bunch of atoms. Like if you're using like a Rietveld refinement or a PDF GUI, you can have like fractional occupancy. RMC profile, you can't do that. You have to have an atom there or not there, and it has to be just one type. So if you have like a mixed occupancy or vacancies, then there's steps you need to take in order to basically get rid of those. And there's steps to do that, and I'll actually go through this with you this afternoon on how to do that. But basically what you can do is you can run RMC profile without any data. So it's not actually fitting any data. And what you can do is you can use, it has a swap command, which you can swap between different atom sites. So if you had like two different elements that are occupying the same site, you would have starting configuration where you have both of them, and they're going to be ordered when you blow it up into a site. But then you just simply run it, swapping the atoms for a while without fitting any data. And the only thing it'll do is just swap the atoms. And so sometimes when you have these situations, you need to do an extra step or two before you run it, before you actually start fitting it against the data. And we'll go through more detail of that later this afternoon. So input files, there's a few ones. There's the DAT file, which is the main control file. It's telling RMC profile what you do. You also have this .rmc6f. This is the name of the configuration file that you make. Then you have your data sets for G of R, F of Q, S of Q. And you can actually use any extension you like on these, so I usually just use those. And then there's additional files if you're going to use brag data. I won't get into that specifically, but that's all documented in the manual. So in the DAT file, what you're going to see at the top, there's a bunch of metadata lines that you should generally fill out. There's a number density. The number density is important because it gives you that, that 4 pi rho 0 background that I was talking about yesterday, which is the actual 0 point for G of R. And that's just calculated from your configuration, just the size of your configuration, the number of atoms in it. So the first thing you really need to choose is the maximum move. So that's how far an atom, the most an atom will move each random move. And this is usually actually a pretty small value. Usually about 0.02 works good. If your configuration is quite far off from what you think it needs to be, you can make this a bit larger at first, and then maybe make it smaller later. Something I want to mention that is not necessarily obvious is that the max move you choose actually will affect how many moves are accepted. So there's a bit of a correlation between the maximum move and the sigma that you choose. Because if you make, say you have a small max move of 0.01, then if you're only moving 100th of an angstrom, if it makes the fit worse, it's not going to make it that much worse, probably, because it didn't move it very far. If you have it at 0.1 and you move it out of 1/10 of an angstrom, it could make the fit many times worse. And so if you have a large one, a large max move, you're going to get less moves accepted, and so you might need to adjust your sigma accordingly to allow more moves to be accepted. So it's important to note that there is a correlation between your max moves and what an appropriate sigma is. So the other thing you need to pick is the minimum distances. And this is important because it keeps atoms from getting unrealistically close to each other. It also keeps the atoms basically in their kind of the general coordination sphere that they were in. So it keeps them from going, totally random on you. And you just have this order here, like a one here. So you'd start with the lightest element, and then it's that correlate distance to itself, to the next lightest, to the next lightest, and then so to this format. And these are kind of examples of how you would do that for two compositions. And this is a little tricky. So what you want to do is you want to pick a value that's reasonable. And I do a couple different things and kind of jointly consider them when I'm doing this. So one thing I'll do is I'll figure out what is a typical value for this kind of bond length. So like if I'm doing like an iron oxide, I'll look at what is the typical iron oxygen bond length. And then you want to subtract from that about, something around usually 0.41 or 0.421 or something. I found this range is kind of good. And that's just what a typical thermal motion at room temperature is. And if you think like, it may be very asymmetric or something, you could give it a little bit more room for there. For neighbors that are further apart, where they're not bumping into each other stuff, you can give it a little bit larger one from the average one. The other thing you want to do is you want to look at the PDF. Like if this is your first peak here, you might set the minimum distance to be right here at the minimum, right there at the bottom, right between it goes up here, because that's going to make the refinement behave normally. And you can see kind of here, like this peak here comes down here and ends, so you might, whatever contributes to this, you say, well, this ends about here, so you might make it here. If you make it a little further down, it might start putting distances in here, and you get some weird differential. So I would do it as a combination of figuring out what a typical distance is and what a reasonable thermal motion around that is, along with actually looking at where you have minimums in the PDF. And generally for the shortest distances, these parameters are very important. For more atoms that are further apart from each other, it's not so important. That will generally take care of itself. And then there's a few other things you have to take into account, like the print period. That's just how often it outputs the progress. I usually just use the number of atoms in the supercell or some multiple of this. The save period, how often it will overwrite all the files. Usually I do that every half hour. And the time limit is how long it runs. So this you need to run it pretty long, and this depends on several things, like the speed of your computer, of course, also how many atoms you have, how close to the starting configuration the actual configuration is. So I would usually start it at the like one day and then come back and look at it the next morning, so run it almost a full day. Sometimes for more complicated things, you may need to run it several days or even several weeks. And there's a paper at the end that I'm going to recommend you guys look at that talks about that I found very interesting. So as I mentioned before, this sigma value is critical for getting a reasonable result. Because if you have a very large sigma where you're just going to accept all the moves and then you're just smearing atoms out and you're not fitting data, and the RMC is really not doing anything. If you have a very small sigma, then you're just going straight to the local minimum, and you're just doing like a least squares refinement kind of, and it's not, you're not really doing anything. So you need to get something where you're accepting a reasonable amount of moves. So you want to be accepting the right amount of poor moves that you're still progressing towards a better fit, but you're also getting out of local minimum. So I found usually maybe something around 50% is good. Anywhere between 30 to 60% could be reasonable. And usually values, I don't know, I would start with 0.03 I found, and you might need to adjust it after you see. So when you first start running it, it's going to accept almost all the moves, because if you have this giant supercell that's highly ordered, you basically don't have any thermal motion, so you have this just delta function trying to fit a Gaussian peak. So it'll accept almost all the moves. Once it's been running for a while, though, it'll kind of settle into something. And then you want to make sure that's reasonable. You're not accepting almost all the moves or very few of the moves. And then if you have multiple data sets, you need to pick a weighting between them. And that can be a little bit tricky. And sometimes you just have to see how the data is being fit and then possibly adjust it if it seems to be fitting one data preferentially to the other one. Because you want them both to have about the same effect on your data. And then if you're using constraints, which usually you are, then you also have to give weighting to those constraints. And you got to make sure that that is high enough that it's actually affecting it, but not too high that you're just forcing it to do what you think it's supposed to do. Because if you're doing that, you're not really doing a fitting. So these are kind of typical values, but sometimes you have to play with that, and you have to see how it's running and if it's doing something reasonable. So as for types of constraints, constraints are often needed to keep the structure chemically reasonable. So the PDF or the RMC profile, will just make the most random distribution that's consistent with the data, and that's why you want to use several data sets if you can, but sometimes that's not enough just because there's still too much freedom, or also, like especially in the case with X-ray PDF, sometimes some of the atoms will contribute very weakly to the PDF, and so it can just kind of move them wherever. So there's a lot of different choices, and this is actually a comprehensive list, but you can find a whole list of them in the manual. One of the best ones is the bond valence sums, and I like this one because it's flexible in terms of the bond lengths. It's not forcing the bonds to be any particular length, but as long as the overall bonding is chemically reasonable, then it's good. You can also set distance windows, which is basically just an addition to the minimum distance constraints that you have to put, where it also has a maximum distance. So any atoms that are close enough to start with can't get further than a certain distance apart. You can also keep interatomic potentials, which basically just is like